Yeah, so everyone's quite happy with the first step. What have I done with my nice pen? Okay. So nitrogen lone pair comes in and attacks the slightly delta positive carbon, kicks off the bromine, but nitrogen's used its own private stash of electrons, so yeah, it's got a positive charge. So we need to get that positive charge back. Simple way to do that is to break that nitrogen-hydrogen bond and give nitrogen the electrons. You will see in various places, online, in books, that the NH3 then comes along and picks off that H+, which actually is probably what happens, but it's not an AQA marking point. So if you don't put it, you still get full marks. Okay. Yeah, and obviously then we go on to make this, which was, well, we've seen that recently, haven't we? That ethyl amine. Why are we interested in it? Because, well, we know it's a stronger base than ammonia, right? But stronger base, remember our stuff about Lewis bases? Lewis base is one which donates a lone pair of electrons, and donating a lone pair of electrons is an awful lot like a nucleophile, isn't it? And if that's a stronger base than ammonia, and it's better at donating its lone pair of electrons than ammonia, then it'll be a stronger nucleophile than ammonia. And if it's a stronger nucleophile, then when it bumps into a molecule of bromoethane, it all kicks off again. So that's going to come in there, and that's going to come in there, and then there'll be da-di-da-di-da stuff there, losing a hydrogen, and we'll end up with what? We've now attached that nitrogen to that carbon as well. So that nitrogen is now attached to two carbons. So we've got a di-substituted diethyl amine, which means we've got twice as many alkyl groups contributing electron density with a positive inductive effect, shunting it down to the nitrogen there, which means it's going to be a stronger nucleophile. Might not be a stronger base because it's not soluble, but it'll still be a stronger nucleophile, which means it's all going to go again. Here's our NH thing, and that's going to come over here, and that's going to kick off another bromine, and yada 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 yada. What are we going to end up with now? Three ethyl groups. Yeah. Wow. One was better than none, and two's better than one. Three's even better than two. Well, hang on, we haven't got any hydrogens to lose. You know, we know this step here is important. Well, doesn't matter, because nitrogen's still got a lone pair of electrons. So we can still go again. La-di-da-di-da. Oops, that's not positive. It's got a lone pair. There we go. Whee! Bonk. What do we make now? What's our product now?
Is it
Yeah. How's that going to work though? Because nitrogen's only got 3 bonds normally. What's it going to form? Tetraethyl what? Tetraethyl's the right start to its name, by the way. me finish this formula. That's not finished. Hey? Okay, so yeah, that must have a positive charge because it's given up its lone pair of electrons, but that's okay because we've got lots of bromide hanging around to make that. Okay, so what's that called? You started us off with tetraethyl. We did this right at the beginning when we were doing naming. So we talked about primary amines, secondary amines, tertiary amines, and quaternary what? Salt. Okay. What was the word that goes in between quaternary and salt? Ammonium. Okay, so that's tetraethyl ammonium bromide. Tetraethyl ammonium bromide. Okay. Right, so there's sort of 2 points here. The first is this is just a complete mess. And if we're doing anything in organic chemistry, we don't want to make a mess. We want to have a couple of reactants that react in a nice, clean reaction and give us mostly one product, which we can then purify and move on. And we don't want lots of hideous side reactions taking place that are going to give us 1, 2, 3, 4 products in a big sort of mush. So if we just want to make the primary amine, the ethyl amine, how do we tip things in our favour to make the reaction work for us and not do all these other side reactions? Go on.
That reaction only takes place when there's an excess of ammonia. So if you
Okay,
don't have
well,
that,
all reactions will take place all the time.
yeah.
But if we have excess ammonia, then, and we'll use a huge excess of ammonia, like 100-fold excess. And fortunately, ammonia is very, very soluble in water. You can get an ammonia solution called 880 ammonia, which is the concentrated form of ammonia. It's called 880 because that's its density. It's got a density of 0.88. That's how much ammonia is in there. Completely changes the density of the solution. But we can then use that as like 100-fold excess. So even if ammonia does make a molecule of ethylamine, well, there'll be 100 times, more than 100 times the ammonia molecules left in the solution. So bromoethane is much more likely to bump into an NH3 than it is a product. So that's the first thing. So we use excess ammonia to stop the, I'll just call them the side reactions taking place, and only forming the primary amine. Okay, so that's going to be something we want to do sometimes. Just give me a moment. Just need to look up bentremonium. There it is. Yes, accept all cookies. Oh, what was that? Lovely. Just going to pop this down there so everybody can have a look at what's going on. Okay. Sometimes, however, we might want to make a tertiary ammonium salt. And this is one of those compounds. So we can imagine we'd start off with a big long chain of primary amine and then mix it with an excess of bromomethane. Again, if we had an excess of this, well, we're going to make that, aren't we? So if you started off with a big long chain molecule with a nitrogen on the end and then reacted it with an excess of bromomethane, we'd end up with that bad boy there. Why do we want to make that? Looks like a kind of funky molecule. Well, the reason we like that is it can be used as, quaternary, how do you spell quaternary? Quaternary, there we are. Ammonium salts as hair conditioners. And fabric conditioners as well. Okay, so it's important we all have good hair care routines. I'm sure you have bottles of hair conditioner sat around the bathroom somewhere at home. So this is a common molecule, benhydramonium chloride, which is used in hair conditioner. What it does, and I realise I'm talking to an audience of people with mainly short hair here, so there's probably not an awful lot of people that have had trouble brushing out your tangle in the morning. You might have other people in the house who have that issue. The thing about hairs is that the molecules in the hair have slight charges on them, and then they can attract each other, and then you get that sort of static attraction. They get that, then they get tangled. So to stop that, you use a hair conditioner. So here's your hairs. Okay, what the conditioner does is the little charged nitrogen on the end there fixes onto the hair follicle, and then the long carbon chain, that big long chain of methyls, sort of coats the hair follicle like that. Because we've only got carbon, hydrogen, alkyl groups here, we've only got those weak van der Waals forces between one of those chains and the next, so they tend to stay apart. So that means that the hairs don't stick together and go all staticky anymore. They tend to sort of fall apart in a nice way, when you're brushing your hair. The same thing happens in fabric, right? That's why fabric softeners or fabric conditioners make your clothes, your nice fleeces feel lovely and soft, because all the hairs are all sort of apart rather than being stuck together in little hard clumps. Okay. However, there's a problem with using fabric conditioners on towels. Can anyone see why towels and fabric conditioners don't go together so well? I mean, we all like those really lovely, big, fluffy, soft towels, don't we? But what would be the problem with covering the towel strands with long, non-polar molecules? Yes? Yeah, the water will flow off them. So those lovely, big, soft, fluffy towels are not actually very good at absorbing water, which is kind of what we need towels to do. That's their job. So when you're washing your towels, when you're doing your laundry, this is a good laundry point as well. We've got some good domestic science going on here. When you're doing your laundry, don't put your towels in with your other soft fabrics that you're going to put fabric conditioner in. Keep your towels separate for things that don't use fabric conditioner. Okay, otherwise they'll get lovely and soft, but they won't dry you very well, which again is a little bit disappointing. Okay, we learned some really interesting things today.